The world of communications and connectivity are growing at breakneck speeds, and ESPEC is rapidly supporting the development of the world's most advanced technologies by providing optimal test environments that contribute to the development of 5G and IoT technologies. In this video, we will deliver an introduction to our environmental test chambers and measurement systems specifically for the IoT, 5G, and optical communications markets, fleshing out the difference between 4G and 5G, standards, applications, challenges, and device issues, and how ESPEC delivers solutions. We genuinely hope this information will support your successful business goals. I am Cami Page, Marketing Manager for ESPEC North America, and it is my pleasure to facilitate our presentation and share the platform with our presenter and knowledgeable product specialist, Mr. Alan Aronson, in just a moment. But first, a bit about us. ESPEC Corporation is headquartered in Osaka, Japan, and boasts a strong financial position with $228 million in sales, over 1,500 employees, and 75 years in business. ESPEC Corp primarily manufactures temperature and humidity environmental chambers for all industries: telecommunication devices, automotive, home appliance, semiconductors, contributing to R&D, and reliability test use. ESPEC provides environmental test chambers and measurement systems all over the world for increased efficiency in the evaluation of test standards, enhanced reliability, improved temperature characteristics, and superior antenna performance. As pioneers in the field of environmental testing, we bring decades of experience and expertise to your quality and reliability goals. Our network of sales, service, and support span the globe and allow for stable procurement of refrigerants around the world that enable us to provide high quality and environmentally friendly products and services to our customers. We strive to be a highly trusted global company and partner. We also distribute all over the world, serving more than 50 countries. So you can be confident that wherever you design, test, manufacture, or potentially relocate, we are able to support you. ESPEC's North American operations have been independently operated and firmly rooted since 1983 and include manufacturing in Michigan and Colorado, with sales, support, and service from coast to coast. Now that you know a bit about who we are, it is my pleasure to introduce Mr. Alan Aronson to dive into the heart of our presentation and how we can serve you and solve your 5G IoT testing needs.
Thank you, Cami. First, let's start with the differences between 4G and 5G. This slide summarized it in 3 significant criteria. The first is speed. 5G is much faster than 4G, with up to 20 gigabits per second. With this speed, you can download a 2-hour movie in about 3 seconds, whereas it took 5 minutes with 4G. Second is latency. Latency is the time which it takes for a signal to reach the other end. It's 1/10 of that of 4G. If you're a gamer, you know what that means and how important it is. Ultra-low latency means there's no lag between what you see on a screen and your reaction. This would allow you to control devices in remote locations with precision. The last one mentioned here is multiple simultaneous connections. With 5G, you can connect about 100 times as many devices or sensors to the network simultaneously. If you go to Amazon, you can find more and more smart whatevers. We see smart appliances, smart watches, smartphones, and all these devices released daily. But 5G is capable of handling all of that. In other words, 5G is a technology that will play a vital role in the infrastructure, giving a cue to the arrival of the true Internet of Things, artificial intelligence age. As I mentioned in the previous slide, 5G is much faster, has less latency, and allows more devices on the network simultaneously. Aside from that, the big difference is its application. 4G has been used mainly for communication between people in person-to-person communications. Yes, it was used for person-to-machine or P2M communications, but mostly limited to alarm notifications. Examples of usage are surveying support in civil engineering, car navigation systems to support drivers, etc. The communications were limited to a supplementary level where people are present. So even if there are failures, the damage was limited. You always have someone present to fix the issue. However, with 5G, its application will be greatly expanded. For example, it can communicate with or control machines in remote locations or in extreme conditions where it may be too harsh for people to work. It can also be used for communications between autonomous vehicles, roads, toll booths, and other infrastructure. As 5G grows, its use will go further into machine-to-machine communications where human intervention is not present. If anything goes wrong with no one around to fix the failure, the damage could be extensive. In other words, system reliability is critical. We need a clear definition when we talk about 4G, 5G, or whatever. And the organization that defines the use of these words is 3GPP, or Third Generation Partnership Project. 3GPP was established back in 1988. Its scope was to produce technical specifications and technical reports for a 3G mobile system based on evolved GSM core networks and the radio access technologies they support. Later, the scope was amended to include the maintenance and development of the technical specifications and technical reports for evolved 3GPP technologies beyond 3G. 3GPP uses a system of parallel releases, which provide developers with a stable platform for implementing features at a given point and then allow for the addition of new functionality in subsequent releases. As of right now, up to release 16 are frozen or fixed, and 17 and 18 are still open. Release 18 is not the end. The development is continuous and is not ending anytime soon. This slide describes the change in technology from 4G to 5G. We will cover four major areas. The first is a technology called multi-element antennas. In 5G, the distance the radio waves travel will become shorter as the frequency increases. So technology called beamforming will be used to extend the distance. Up to 4G, radio waves were sent evenly across the area. But beamforming narrowly focuses radio waves and concentrates them in a specific direction, which requires many antenna elements. The second is low dielectric materials. As the frequency used becomes higher, transmission loss increases. To minimize the loss, low dielectric materials are required. Third is miniaturization of everything. For example, the short travel distance of high-frequency waves used in 5G will require many base stations, both indoors and outdoors. Since the installation locations are limited indoors, the base stations should come in smaller sizes and weights. This leads to the fourth topic, high density. To achieve small size and weight, all parts and components used in these devices must come in smaller packages. Smaller packages mean denser circuits, integration, or merger of function, and reduced use or elimination of connectors and wires. So here is the summary. The standard body 3GPP will continue with specification development of 5G. The specifications of 5G are not complete, and development will continue. 5G technology is more extensive than its predecessor, and ensuring system reliability is critical. The technology itself asks for better, more suitable materials and design. The industry faces these issues: heat generation, performance and reliability tests by over-the-air high-frequency temperature characteristic tests, extreme condition use, and all these in a shorter development cycle. This brings us to our second topic, 5G device issues and ESPEC chambers. Let's discuss thermal management. 5G requires a large amount of data processing and high processing speed due to the increased power consumption and heat generation of the processor. To remove the heat, we can add components such as cooling fans, but this may increase the cost, and 5G devices are often required to be small, with no space for cooling fans in a smartphone or other small devices. Therefore, heat generated by the CPU is dissipated to surrounding components to lower the temperature, and high heat resistance is required for each component in many cases. In this way, thermal management is being taken for each device, such as communication terminals and base stations, but high heat generation will continue to be one of the major issues for 5G devices in the future. It requires not only to suppress the heat generation, but also to operate normally, even when the heat is being generated and the temperature is high. Therefore, it's necessary to test the reliability of components under high temperature conditions. Next, I would like to talk about ensuring reliability and shortening the development period. 5G is not only a way of communication, but it will also become an industrial foundation together with AI, IoT, image processing, and semiconductor industries. In the design stage of 5G related products, in addition to thermal management, joint reliability evaluation is becoming more important than ever. This is an example why junction reliability evaluation is required. Smartphones and tablets have a very high density of components mounted on them, and they are facing many situations, including high temperature when operating and low temperature when they're powered off. This causes the board to expand and contract repeatedly. This increases the possibility of solder cracks and other problems caused by thermal expansion and contraction of the board. For this reason, it is important to perform temperature cycle tests and thermal shock tests for reliability. ESPEC can recommend several different test chambers. We have various types depending on the size of the sample and heat generation. The small type has a capacity of 680 liters to 1100 liters and can tolerate up to 11,500 watts of heat generation from devices while maintaining a temperature environment of minus 20 degrees C. The large type has a capacity of 65 cubic meters and can tolerate up to 76,900 watts of heat at minus 20 degrees C. We offer the best chamber solutions for reliability testing of high heat generating devices for 5G. We have a wide range of chambers for temperature change and thermal shock testing, including a rapid temperature change chamber that stresses devices with a constant temperature change, and a thermal shock that can rapidly change the test temperature to apply thermal stress. We can provide chambers to meet various standards. Depending on the device, it's possible to quickly determine the failure mechanism by applying higher stress, which can contribute to shortening the test and development time. Our next topic is the temperature characterization test over the air, or OTA. Prior to 4G, antennas and communication modules were separated, so typically they were checked separately. Just as the performance of antennas were checked in an anechoic chamber to prevent reflection of radio waves and ensure accurate testing, the performance communication modules was checked in a constant temperature chamber for temperature characteristic testing. However, in order to reduce transmission loss due to the higher frequency of 5G signals, the antenna and wireless communication module will now be integrated as shown in this figure. And it will be necessary to conduct temperature characterization tests and performance evaluation wirelessly, or OTA. We're going to introduce the best chambers for over-the-air testing, or OTA. The following pages will cover a few details for each chamber system. This is an anechoic temperature room. The attenuation rate of 60 dB or more can be obtained in the frequency range of 0.5 to 30 gigahertz. The feature of this system is that the turntable and positioner used in antenna performance tests can be operated at low temperatures without freezing due to our unique heat insulation technology. This next system is the anechoic temperature chamber. This chamber has an attenuation factor of more than 50 dB in the 0.7 to 6 gigahertz band. If you have requests for frequencies beyond those mentioned, please contact us for further information. This slide is an introduction to equipment for evaluating the temperature characteristics of dielectric constant. There are two main methods for evaluating the temperature characteristics of dielectric constant: the S-parameter method and the free space method. At this time, the S-parameter method is under development and is only being offered in Japan. We plan to expand this to other markets in the future. Regarding the split cylinder method, this device can be installed with the split cylinder resonator on our benchtop chamber and can also be set up on a tabletop as shown in the figure here, making it possible to build a test environment in a very small space. As an introduction to other related equipment, we can provide environmental test equipment with EMC measures. In the past, when testing communications terminals and modules, it was often necessary to set up the temperature chamber in a shielded room in order to prevent radio wave leakage from adversely affecting the building's communication environment. Now we have a chamber that can prevent radio wave leakage from the specimen by itself, without being installed in a shielded room. By adding the shielding capability to the chamber, this makes it possible for customers to implement EMC measures without having to install a shielded room. That's our lineup. We have a wide range of products to meet various customer needs, so please contact us for more information.
Thank you, Alan, and thank you for joining us. You can always access us online for product information and technology support at espec.com or email us directly at sales@espec.com. Thank you.